Learn like a pro.
All right, today we're diving into one of the most brilliant factory optimization puzzles ever solved, the Haber process. Now, this isn't just a chemistry lesson, it's a masterclass in engineering, economics, and finding a clever compromise that literally changed the world.
So, let's start with a huge question. A planet-sized question. How do you feed billions and billions of people? This is a massive production challenge. You need something reliable, efficient, and affordable on a global scale. Where do you even start?
Well, the answer is fertilizer. And the one ingredient that modern agriculture absolutely depends on is ammonia. Yep, our entire global food system is built on our ability to mass produce this one little molecule, NH3.
But, and this is a big but, making ammonia is tricky. The problem is baked right into the chemistry itself. It's something called a reversible reaction, which, if you're trying to run a factory, is a huge headache.
So what exactly is a reversible reaction? Well, it's pretty much what it sounds like. It's a chemical process that can run forwards and backwards. You're trying to make your product, but at the very same time, your product is trying to turn itself back into the raw ingredients you started with. And this slide shows you the nightmare scenario perfectly. On the left, you've got the forward reaction. Nitrogen plus hydrogen makes our valuable ammonia. Awesome. But at the same time, on the right, you've got the backward reaction happening, where that ammonia is just decomposing. Imagine running a car factory where as soon as the cars roll off the line, they start falling apart back into steel and rubber. It's an efficiency disaster.
And this leads us to the heart of the engineering problem. To make this whole thing work without going broke, you've got to find the perfect balance between two things that are fighting each other. How much stuff you make, that's the yield, and how fast you can make it, that's the rate.
So let's put you in the control room. You've got the dials for temperature and pressure right in front of you. Your job is to make the most money. So what's the smarter move? A slow process that eventually gives you a whole lot of product? Or a super fast process that only gives you a little bit at a time? This is the fundamental trade-off of the Haber process.
This table really lays out the whole dilemma. You want a better yield? Okay, you can crank the pressure way up. The problem? That is incredibly expensive. We're talking fixed steel pipes, massive compressors. The cost to build the plant would be astronomical. Okay, what about option 2? Lower the temperature. That also gives you a better yield. But it makes the reaction so agonizingly slow that it's completely useless for business. You'd go bankrupt just waiting for the first batch to finish.
So the most important thing to get here is that the solution isn't about finding the perfect conditions according to a textbook. No, it's about finding the most economically viable compromise. You need a yield that's good enough, happening fast enough to actually turn a profit.
And here it is. This is the sweet spot they found. A pressure of 200 atmospheres, which is super high but manageable, and a temperature of 450 degrees Celsius. Hot enough to get things moving, but not so hot that it pushes the reaction backwards too much. But the real hero here is the iron catalyst. Think of it like a chemical matchmaker. It helps the nitrogen and hydrogen react way faster than they normally would, which means you can run the whole thing at a much lower and cheaper temperature. Okay, so we've got our settings dialed in. Now let's take a walk through the factory and see how this all fits together in one of the most elegant industrial processes ever designed.
First up, you need your ingredients. The nitrogen's the easy part. You just pull it out of the air we're breathing, since air is about 78% nitrogen. The hydrogen's a bit more involved. It's usually made by breaking down natural gas or other stuff from crude oil. So here's the play-by-play. First, you mix nitrogen and hydrogen gas in a very specific 1:3 ratio, and you compress the heck out of it. Then you heat that pressurized gas up and pass it over the iron catalyst. Now the gas that comes out is a mix of ammonia and unreacted gases. You send that mix into a cooling chamber, and here's the clever part. Ammonia turns into a liquid at a much higher temperature than nitrogen or hydrogen do. So the ammonia condenses, you drain it off as a liquid. But what about the leftover gas? Well, that's where the real genius is. Because after all that, the intense pressure, the heat, the special catalyst, the gas coming out of the reactor is only about 15% ammonia. 15%. In most industries, a 15% conversion rate would get you fired. It sounds like a total failure. So how on earth is this profitable?
The secret weapon is the recycle loop. That 85% of unreacted nitrogen and hydrogen, it's not waste. You just pipe it right back to the beginning, recompress it, and send it through the reactor again and again and again. By constantly recycling your raw materials, you waste almost nothing, pushing the overall efficiency of the entire process up to an incredible 98%.
It's a brilliant, elegant solution to that low-yield problem. So now we've successfully made all this liquid ammonia. Let's look at where it goes and why it's just so important.
The vast majority of the ammonia made in these plants has one destination: farms. It's the key ingredient for nitrogen-based fertilizers, like the ones you see here. These compounds give crops the nitrogen boost they need to grow big and healthy, which, you guessed it, feeds the world.
And you should know this whole puzzle of taming a reversible reaction isn't unique to making ammonia. The contact process, which is how we make sulfuric acid, another incredibly important industrial chemical, has to solve a very similar problem. Learning how to manage these kinds of compromises is really what modern industrial chemistry is all about.
And here's a fascinating final thought on that whole reversibility thing. The chemistry doesn't just stop at the factory gate. If you add something alkaline to soil that has these fertilizers in it, something like lime, you can actually kick off the backward reaction. It causes the fertilizer to break down and release its ammonia back into the air as a gas. It's just a great reminder that these chemical principles have real-world consequences out in the environment.
So, when you step back and look at it, the Haber process is just a masterpiece of engineering. It's a finely tuned compromise between chemistry, physics, and pure economics. For more than 100 years, this single solution has been the bedrock of our ability to feed a growing planet. It really makes you wonder, as we face new challenges with energy and sustainability, what's the next great engineering compromise that's going to change our world?